Hey, 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 welcome back. Welcome back to our Chegg Gen Chem office hour tonight. I'm super excited to be here with you all again on this Thursday evening. Again, I am Janita Pritchard, or Dr. J, and you can follow me at Gen Chem with Dr. J. I'll be your virtual instructor for tonight's office hour. So for everyone that might be new to Chegg or your first office hours, welcome. And for anyone that has been here before, welcome back. A little bit of background information about me before we get started. I have been teaching general chemistry in some form or another for the past 2 decades. I actually have a PhD in analytical chemistry and also run a nonprofit that introduces K through 12 students to STEM, which is science, technology, engineering, and math concepts through hands-on exciting activities. I launched my online platform, Gen Chem with Dr. J, to support students all around the world as they navigate their own personal journeys in chemistry. I'm super excited to partner with Chegg over the next few weeks to host these live office hours. For those of you that might be new to Chegg, they're here to make your academic journey a bit smoother. And you can actually scan that QR code in the top corner to learn more information. But they have tons of resources to help you get through school, like online study help, expert Q&A with step-by-step solutions, writing support, and a whole bunch more. So again, if this is your first time joining us, welcome. Hopefully this won't be your last. And if you've been here before, welcome back. Can't wait to hear your questions that you have coming through. But I'll be here to go through step-by-step questions. So I want to hear from you. I want to know what is it that you're struggling with so I can help you out along the way. You know, I feel successful when you all feel successful. So please feel free to drop comments in the chat, questions that you want to learn more about so that we can learn together. We're going to kick things off in just a minute, but I want to make sure that everyone has the tools that they need to be successful in today's office hour. So first and foremost, as we're doing a chemistry class, strongly recommend that everyone has a periodic table somewhere nearby. I've printed mine out. You might use your phone if you're not using your phone for viewing, but definitely have a periodic table nearby so that we can make sure we're looking at the same information together. Also, I recommend that you have a calculator nearby. Doesn't have to be a fancy calculator. As long as your calculator can do exponents like 10 raised to the power of something, then you'll be good to go. And so you'll want to follow along as we're doing the calculation so that if you are struggling with putting it in, we could try to troubleshoot it in real time. Okay. So again, if you have questions, please feel free to drop them in the chat and we'll be sure to answer them along the way. Now, a few of you actually reached out to me after my last live from last week and wanted to learn more about the mole. You know, you heard me talking about it, but you wanted to do a few more practice problems. So we're actually going to start there tonight to pick up that conversation about what the mole is and how do we use it when we're doing chemistry problems. When I was taking chemistry classes many moons ago, this was one of those subjects that once I understood how to do it, I felt so accomplished. And so I'm hopefully going to share a couple of tips or tricks that you can use along the way to help you not only understand the mole, but then also set yourself up for success when you're doing your calculations. Okay. So again, if you have questions beyond what I'm covering, put them in the chat and I'll be sure to get to them throughout today's session. Okay. And so the mole, we hear this concept all throughout chemistry class, right? We hear the mole, we hear molarity, we hear molar mass, right? The mole is all around us, but what does that thing mean? Okay. And so I want you to, challenge the way you view this and really compare it to something that you already naturally know a little bit more about, right? So the mole is just a way that we count things. And it's basically a term that we use that represents a certain number of things every single time we say that we have a mole, okay? This is nothing new to you, right? Have you ever said a dozen, right? Every time you hear the word a dozen, you've always been programmed to know that 1 dozen, regardless of what we're talking about, we would always say equals 12. I have 12 of those things, unless it's a baker's dozen, then we got 13, but never mind that. All right, so 1 dozen means 12. And I could have 12 eggs. I could have a dozen cars, which means I have 12. I could have a dozen shoes, which means I have 12 shoes, right? Every time we've heard the word a dozen, we know that when I'm counting it, that means I have 12. And so again, I could have 12 eggs, or I could have 1 dozen. If I said shoes, that means I have 12 shoes. Or if I said I have 1 dozen cars, that means I have 12 cars, okay? And so this idea of using a term to count something is something we're familiar with. Well, in chemistry, we do the same thing, where anytime we hear 1 mole, that represents a lot of things, right? It actually represents a huge number of things, but we'll get to that in just a minute, okay? But I wanted to connect one other concept to you before we get into the counting aspect, okay? Now, again, we know 1 dozen means 12. Now, just because I have 12 of those things, whether it's 12 eggs, 12 shoes, 12 cars, or a dozen of each of those, do they all add up or have the same mass? Do they all weigh the same amount? You should probably say no, right? They all are going to weigh something different. 12 cars is certainly much heavier than 12 eggs or 12 shoes, right? And so the mass of those is going to change, right? So there's some amount of grams of eggs that would be in a dozen, some amount of grams of shoes that would be there, some amount of grams of cars, right? And obviously, as we get into that car scenario, a lot more. So if that concept made sense to you, the fact that 1 dozen, anytime we count, means 12, and that each of those dozens will have a different mass associated with it, that's the same thing that's happening with how we use the mole, okay? When we say we have 1 mole of something, 1 mole is how we're counting, right? And so we use this to count really, really, really tiny things like atoms and molecules, these things that we can't see with the bare eye. And so 1 mole is equal to a certain number, which is called Avogadro's number, which is 6.022 times 10 to the 23rd. So that's a huge number, right? And we could say we have that many atoms of carbon, or I could say 1 mole would be equal to 6.022 times 10 to the 23rd atoms of, let's pick an element, nitrogen, okay? And so yes, when I'm counting those things, that's how many I have. But just like the dozen example where our eggs, our shoes, our cars all had different masses, these atoms or molecules or whatever we're counting will all have different masses as well. And so where do we find the mass for those? Well, fortunately, the periodic table is what's going to help you out. When you're looking at how much mass is in a mole of something, that's where your periodic table, you're going to actually go to the mass that's found on your periodic table, not the whole number, but the number that likely has the decimal point associated with it, the atomic mass. And you're going to set that equal to 1 mole. So if we're saying we have 1 mole of carbon, its mass, find carbon on your periodic table, would be 12.011, and then we're going to say grams of carbon is in 1 mole. Or if we wanted nitrogen, 1 mole of nitrogen would be equal to find nitrogen, which is 14.007 grams of nitrogen, okay? And so it's that relationship, how much mass is in a mole or how many things are in a mole, how many atoms or molecules or whatever thing we're counting, that we're going to be using as we do these chemistry problems, okay? Now, this relationship here, the grams to mole relationship, that's what's known as our molar mass. All right, so anytime you hear the molar mass, it's basically saying how many grams of something per 1 mole. Okay, so grams per mole. And this relationship over here, the fact that 1 mole is equal to 6.022 times 10 to the 23rd of whatever we're talking about, that is Avogadro's number. I like to call it AV's number, okay, that we use for counting, okay? And so when we're doing this, one trick that I like to use is this idea of mole island, which is a visual way to think about how I need to set up my calculations, okay? First off, we're still going to be using that given and find format that I introduced to you all about 3 weeks ago or so. And so a lot of these problems, we're going to be given something that we're trying to solve for. We're trying to find what it equals to. And so we're going to follow that same format where we're going to take our given, we're going to put our units on the bottom and solve for whatever we are the problem asks for. And sometimes we might have to do multiple setups if, let's say, there's not a direct connection between one and the thing we're starting with and the things that we're solving for. Okay. But how to know how many of these brackets, these conversion factors we need, this is where this trick, which is called mole island, will help. So mole island is a quick visual that I like to draw. And when I was in class, I used to literally draw this on my tests so that I didn't have to think about it whenever I got to doing the question. I would draw this out because then I can use this to help me map out my problems. And so I put mole in the center. On the right side, I put an island that represents my grams. And on the left side, I put an island that's going to represent the things that we are going to count. And so I'm going to put things like atoms here, how many atoms might be somewhere. We're going to put molecules as an option because that's what we're counting when we're dealing with the actual compound. I'll put formula units here because that's what we count whenever we're dealing with ionic compounds. Okay. And there's actually a top part to mole island, but I won't get into that just yet. Well, maybe we'll get into that next week, what goes on top. But what this picture helps us to understand is, well, can I go from grams to atoms or atoms to grams in one step? And what this picture is showing us is that no, I actually have to go to moles first because that's the connecting unit. That's the thing that links to both sides, right? I know how many moles and grams, that relationship, which is the molar mass. Okay, so that we pull that from the periodic table and set that number equal to 1 mole. And then when I'm going from moles to atoms or moles to molecules, I use Avogadro's number. That's 6.022 times 10 to the 23rd. Okay. But again, what this shows you is if I'm given grams and asked to solve for atoms, I can't do this in one step. I would have to first get to moles, pass to moles first, right? Get to moles, and then I can continue on to my atoms. Okay. Okay, so again, I like this little picture representation because it helps something I can reference very easily when I'm doing problems. Okay, so now let's put it to the test. Okay, so the question here says, what is the mass of 4.78 times 10 to the 24 NO2 molecules? So that's nitrogen dioxide. Okay, and so for me, I'm a person, I like to kind of underline what the question is even asking. All right, so I have 4.78 times 10 to the 24 NO2 molecules. And so that's my given. Molecules. And always write out the full set of information that's given because that NO2 is going to be important when we get ready to solve this problem. Okay. And then I'm asking for the mass. And remember, mass, when we hear mass, that means we're looking for the grams, right? So how many grams of NO2 are present? And so this is where if you drew your mole island, right, this is going to tell us how many steps is this going to take. So I just draw it in the corner. Like I said, I would have this on my tests somewhere or like a scratch paper, molecules here. And so what this shows me is I got to do 2 steps. I got to go from molecules to moles first, and then moles to grams. Okay. And so that tells me I need 2 brackets like this. Okay. And then we're ready to start plugging in information. Again, I always stress, put the units in first. Let the units guide where numbers should go. If we're starting with molecules of NO2, if I want to get rid of that, that means it's going to go on the bottom, molecules of NO2. And remember, I'm not going to grams first right now. My intermediate, that between step, I'm going to go to moles first. I always tell my students when you're doing these types of problems, if you're not in moles, your first step probably is going to be to get to moles first because that's the connecting unit to everything. And then from there, once we have our moles, we're going to work to get rid of the moles. So that'll go on the bottom. And then what we're solving for, the grams of NO2 goes on top. Now we're ready to take the information we know, the connecting units, and plugging it in. So the first conversion, I'm going from molecules to moles. And so here, this is Avogadro's number. I'm connecting how many of these molecules are in 1 mole. And so I'm going to put the 1 on top with the moles, and then Avogadro's number with the molecules. So 6.022 times 10 to the 23rd. And then I need to go from moles to grams. And so that relationship, that's the molar mass. And so, wait a minute, I don't have my molar mass. It's not given to us in the problem. Where do I get this information from? Well, this is where your periodic table is going to come into play. You have to look up the mass of both your nitrogen and your oxygen so you can get that mass correctly. If we look up nitrogen, nitrogen is 14.007, and oxygen is 15.99, or we can say 16. But we have 2 oxygens. So we actually need to multiply that number by 2 in order to get our total mass. So pull out those calculators. I do 16 times 2 plus my 14.007, and that gets me 46.007 is the mass, the molar mass, right? And so now I'm going to put that number up top with the grams. This is why I always like to put the units in first, so I don't have to worry about, am I putting it on the top, on the bottom? Where does it go? Let the units drive it. So you put your 46 on the top, and then is in 1 mole. Okay. Now, once you have it set up, you're ready to do the actual math. And so when you're plugging this in your calculator, anything that's on the top of the bracket, hit the multiplication sign for. So act like a typewriter, go straight across. 4.78 times 10 to the 24 times 1 times 46.07. Then divide by whatever's on the bottom. So divided by 6.022 times 10 to the 23rd, divided by 1. Okay, so plug it in your calculators and let me know what y'all get. This is a good example also to help us see if you're putting things in your calculator, specifically those scientific notations, correctly. Because if you are not, you're going to get a number that looks kind of right, but the exponent's going to be super big. Okay. And so plug it in. All right. And what I'm getting when I plug this in, anybody want to try, see what you get for those that are following along? All right. What I'm seeing is I get 365.183, a bunch of numbers. But because of sig figs, we would be stopping at 3 sig figs. So the answer we would report out is 365. Okay, did you all get that right? Okay, hopefully you were able to follow along with that. I am seeing some great questions coming through in the chat, so we'll get to those in just a second, but I'll pause there just to make sure people were able to follow along with that first problem. Okay. All right, let's go to our questions in the chat and let's see what we got here. All right, I see DC on YouTube has a question about electron configuration. All right, let's talk a little bit about electron configuration. That's a great question, DC. And so electron configuration, this is how we account for how many electrons are found within an atom. Okay. And there's a convention and a set of rules that we follow in order to help us out when we're doing electron configuration. Okay. There's a couple of rules that talk about how many electrons each orbital, which is like the house where electrons live in, how many electrons each one can have. There's a rule that talks about the energy levels, how we're actually going about and filling our energy levels. Okay. And I'm just going to give you really like the short and simple way to do this. Okay. So what I like to do is I look at my periodic table. Okay. And so imagine this is your periodic table. Actually, let me draw that just a little bit lower. All right. So that's like your periodic table. Okay. And there is these really like four main sections that are on your periodic table. Okay. Now, again, this little trick, this way I'm going to set this up is what I use to help me out to do any electron configuration pretty much. It's almost like foolproof. Okay. And so each of these main blocks that you see represent different subshells that exist. So these subshells are the types of orbitals that can exist within an atom. So again, orbitals are basically like the house or the region where electrons reside in an atom. And there's four different types. There are your s orbitals. Okay, so you have s orbitals, which are, and I'm giving you a little bit more background information than you need, but they're spherical. They're really small orbitals. There are p orbitals. So p's look like two balloons connected together, so a little bit bigger. You have f orbitals. Excuse me, you have d orbitals. Your d orbitals look like 8 balloons that have been tied together. And then you have your f orbitals, which are like massive. Okay. And so each of these different orbitals, these are, again, different houses, if you will, that can hold different number of electrons. Okay. And so label your periodic table. Again, I'm a big visual learner. And so I always like to come up with things that make it super easy for me. And so the first two columns on your periodic table, those represent where your s orbitals are being filled with electrons. Okay. If you jump over to the right side, those last 6 columns, those represent your p orbitals. Okay. In the center, these represent your d orbitals. And then on the bottom, those 2 rows that are on the bottom of your periodic table, those represent your f orbitals. Okay. Now, what you're going to want to do is label what energy level these orbitals get introduced at. Okay. And so again, energy levels, quickly, you have your nucleus of an atom. Then these electrons are located a certain distance away from the nucleus. Okay. And so those are what we call energy levels. And so these different orbitals get introduced at different energy levels. And so you're going to put a number 1 by the s orbital at the top, or the s subshell, excuse me. Put a number 2 by the p, a number 3 for the d, and then a number 4 for the f. Okay. And so those are telling me what energy level I could expect these orbitals to be introduced. So 1 is the closest energy level to the next one, so forth. Okay. And then the last trick I'll point out to you is that each of these different orbitals can hold a certain number of electrons. Remember, the s orbitals are very small, they're circular, whereas your f's are like mansions, right? So think of it like a studio apartment, then like a townhouse, a single family home, and then a mansion. Okay. And so your s orbitals can hold up to 2 electrons. That's the maximum you can have in there. Your p orbitals can hold 6. Your d orbitals can hold 10. And your f orbitals, they can hold 14. Okay. Well, this is the cool thing about how the periodic table is set up. Count the number of columns that are in the sections that I pointed out to you. So remember I said my s orbitals, those are represented here by this first 2 columns. We'll count the columns 1, 2. So that represents the maximum number that are in that orbital, right? So there's 2 electrons. Look at the p. Count the columns. There's 6. That represents the maximum I can have in that p orbital. Your d's, which are in the middle, there are 10 columns. And then your f's, there are 14. The one thing I'll point out to you to be careful with is if your periodic table is like mine, which sometimes many of them look like, you're actually, if you count these, it's going to be 15. And you're probably like, wait, Dr. J, you just said it's supposed to be 14. And I'm not lying to you. But these 2, the lanthanum, and actinum actually are really reside right here. So they're not technically, they're the beginning of the series, but those 2 actually reside right here. So your counting goes from 58 to 71. Just trust me, I promise. Okay. All right. So why did I have you draw this thing out? Well, this now tells you, it gives you like a map that you can follow as you are doing your electron configuration. So DC, you asked about the electron configuration for iron, okay? So what you need to do is find iron on your periodic table, and I'll draw a schematic about where it is. It's about like right here on your periodic table. And so when you're doing the electron configuration, you're basically accounting for all the electrons that you pass as you're getting to where that atom is, okay, or where it's located. And so why I gave you those numbers and the letters is because that's now going to tell you exactly what you need to call out in your electron configuration, okay? So let's start from the beginning. If I go to the beginning of my periodic table, you always start where hydrogen is. Again, the number is 1. We're starting at the first energy level. And when I count, it would be technically this helium is actually over here when we're counting. And so that would be 1s2. And so that would actually get me through my helium. So again, I'm counting my columns. After I get through that first row, well, now it's like a typewriter. You go down to the next row. And if I started at 1, that means the next row is in the next energy level. So 1, so we said 1s2, then we would go and say 2s, and then how many do we go through? 1, 2. Okay. All right, now we're ready to hop across the table, and we're going into where the P's are. Now remember, the P's don't start at the first energy level, so we're not going to say 1p anything. We say 2. All right, remember that's why we put this 2 here. So we say 2p, and we're going to count how many columns we got to pass through. So that's going to be 6. So we filled that up, 2p6. Okay, act like a typewriter. Back to the beginning over here. Now we started at 1, 2. So where neon and magnesium are, that would now be 3, third energy level. 3, and we're going to go through the 2. So 3s2. I'm now at magnesium. Hop over. Well, I started at 2 for my P's. Now I go down to 3. Then I say my orbital, P. Count your columns, 6. Okay, now this is where it's about to get fun. Okay, loop back around. Boom. We're following Aufbau principle, which is telling us how we fill these. Okay, so now we started at hydrogen, that was at 1. Lithium, 2. Sodium, 3. Potassium is now at our 4th energy level. So we're going to say 4. We're in the S. Through calcium, that would be 2. Okay. All right. So now we're getting ready to go through the D's. Okay. Now remember, the D's actually start at the 3rd energy level. Okay. So we're not going to use the fact that we're at 4 here. Because there's so many electrons in this D subshell, it actually is able to do what's called, it's able to penetrate into a higher energy level. And so it basically has the same amount of energy as something that's at a higher elevated state. Okay. Nonetheless, this is why we put our marker here. So the number 3. So we're actually starting at 3 for our D. Okay. And then we're going to say D because it's in this region. And then you count across to where iron is. So that would be 3D. 1, 2, 3, 4, 5, 6. And we would say 3D6. Okay. And so that would be our full electron configuration. Now, we also have something called the shorthand or the noble gas configuration that we can do. And so when we're doing noble gas configuration, you're basically saying, if you pick the noble gas that comes before the element, up until that point, the electron configuration is the same, right? We would have said 1s2, 2s2, 2p6, 3s2, 3p6, so forth. And so you find your element that you're asked, which was iron. You go to the noble gas right before it, which was argon. And you put that in brackets. And then you continue on for the rest of it. And so basically that bracket is representing all of this. All of this, that is argon. And then you would just continue on and say 4s2, 3d6. Okay. So I hope that helped, DC, with your question for your electron configuration. Okay. All right. I'm seeing another really great question from Stag on TikTok. Wanting to know, can you please do molar mass percent of elements? Okay. And I think what you're looking for is the, let's give me a new sheet. I'll actually just clear this out real quick. Okay, so I think the type of problem that you're referring to is if I have a compound and if I wanted to figure out the molar mass, the percent by mass of different parts, okay? We can take that NO2 example that we had just used. So NO2. And let's say that I asked for the percent by mass of oxygen in this compound. Okay. Hopefully this is what you're referring to, Stag, on TikTok. So to do this, we would first need to know, so percent, anytime we hear the percent is basically asking us to look at the part divided by the whole, and we times it by 100 to get a percent. Okay. And so in this case, our part represents just the oxygen. You know, what part of this whole thing, this whole compound is just oxygen. Okay. And so for this, we're going to need to know two numbers here. We're going to need to know the molar mass of the whole thing and the molar mass of just oxygen present here. Okay. And so again, pull out your periodic table and you find your nitrogen. We learned before nitrogen was 14.007 and oxygen was 16. But there's two of them, and that two is going to be important, okay? So again, the whole number there, I believe, was 46. 16 times 2 plus 14.007. Yeah, 46.007. This represents the whole. That's how the whole amount of the NO2 that's present, okay? Now the part, so that would go on the bottom. The part would just be the oxygen that's present. Now, if we put 16 here on the top, that would be incorrect because we don't just have one atom of oxygen present. We have two of them. And so we need to put the mass of both oxygens up top because it's asking for us the mass of oxygen. And so we would say 32. There should be decimals here. Sorry about that. Grams of just oxygen is compared to the entire thing. Okay. Okay. And then we would multiply by 100. And so we would say 32 divided by 46.007. And Stag, if you have put this in your calculator, go ahead and tell me what you get as your answer, making sure that you multiply that by the 100. 32 divided by 46.07 times 100. All right. So what I get is actually, okay, I get 69.55% by mass of oxygen. Okay. So while we figured out the grams of oxygen, what if this also, the percent by mass of oxygen, what if this would have asked us, well, what about nitrogen? What's the percent by mass of nitrogen? Well, technically, now that we have one of them figured out, we could do this one of two ways. We could either set up a part to whole ratio for just the nitrogen. All right. So we could put, we said it was 14.07. So we could do 14.007 grams of nitrogen. And again, we don't have to multiply this one by 2 because there's only one nitrogen in this compound. And we would still divide it by the whole amount that's present. and multiply by 100. And so you're going to take 14.007 divided by 46.007 times 100. And you should get 30.45, okay, as your percentage by mass of nitrogen. The other thing you could have done, because there's only these two elements present, the nitrogen and oxygen, is just subtract. You could have done 100 minus 69.55, and that should give us the same answer, minus 69.55. And that does indeed give us the 30.45. So that's a quick way you can kind of check out your work. Okay. Hopefully that helped. Hopefully you got the right answer, Stag, as you were following along. Okay, again, feel free to put more questions in the chat. I'm seeing a ton of questions coming through. I'm seeing hi from Ashish. Hello. Thank you for joining. All right, I see another question coming through from user 297639469344649 on TikTok. That's asking me to explain cations versus anions. Okay, really great question. Fantastic question. Okay, so let's clear out my board. All right. There's some space for us. All right. So cations versus anions. And so cations and anions are can be created from different atoms as they are reacting to form new things. Okay. Typically, cations and anions occur as we are creating what are called ionic compounds. And so that cation or anion, the ion wording means that there's something with a charge. Okay. And so the charge could either be a positive charge or a negative charge. Your positive charge, those are what we call cations. Okay. So cations, these are the way I remember cations to think positive, cats make people happy. Happy is positive. So cations are your positive ions, and anions are your negatively charged ions. And so the way I remember that, anions, when I look at how it's spelled quickly, anions kind of looks like onion if you eat it. While they're delicious, if you eat it too many, you might have bad breath. Bad means negative, so it might work for you. But in either case, when you're dealing with creating ions, whether they're positive or they're negative, this charge is created because, remember, most atoms just naturally, they're neutral, meaning that the positive protons that are found in the atom and the negative electrons that are found in the atom are the same amount. To create an ion, that means that we're changing. We got to change how many of these two subatomic particles are present. Well, one of them we can't change. We don't change the number of protons that we're referring to because the protons are actually how we identify an atom. Okay, so that's kind of set. So what's changing is the number of electrons that are found in that atom. And so let's think about it. If neutral means my protons equal my electrons, for me to create something that's positive, that means I technically need to have more protons than electrons. But remember, I can't add protons in because that would be creating a different element. So the only way to create our cations, that positive, is to actually get rid of some of those negative the negative electrons. All right. So cations are losing electrons. Okay. Whereas anions are gaining electrons for that same reason. That basically means I have more electrons than I have protons. And so I'm going to add in more. Okay. And so how do I figure out whether or not I'm going to have a cation or an anion present? Well, it's really based on two two factors. One is, where is it located on the periodic chart? That gives you a bit of an indication of whether or not it's going to be positive or negative. But then also thinking about the electrons that it has, specifically the valence electrons, okay? And so, again, visual cue. When you look at your periodic table, you have this kind of step region. On the left-hand side, there are metals. On the right-hand side, those are your non-metals. And then your semi-metals are in this little step here, okay? Typically, when you're creating a compound and thereby an ionic compound and creating these ions, your metals are going to lose their electrons, okay? And your non-metals are typically going to be the ones that gain electrons, okay? So now the question is, well, how many? Is it positive 1, positive 2, positive 3? What is the number that they get, okay? So we'll talk about the main group elements first. So your main group are the first 2 columns, and then these last 6 columns, okay? What we're going to focus on are what are called our valence electrons. And so valence electrons, if this is our nucleus, all right, your electrons are found in these energy levels around the nucleus. And that outermost shell, regardless, depending on how many electrons something has, will vary how far that outermost shell is. But the outermost shell is what we call your valence shell, okay? Everything else in this space, these are your core electrons, okay? And it's your valence electrons that are going to be the thing that we're either gaining or losing as we're creating these ions, okay? And so how do we figure out how many valence electrons that we have? And again, this is going to be for these first 2 columns and these last 6. So the column actually tells us how many valence electrons they have, okay? So group 1 means that there are 1 valence electron. Group 2, okay, so group 1 is 1 valence electron. Group 2 is 2 valence electrons. So this is the number of valence. Group 3 is 3, all the way to 4. It's 4 electrons, 5. So it's like kind of really smart how the periodic table is laid out, because there's so many just hidden cues that will help you out as you're doing this class. 7 does not equal 8. 7 equals 7. And 8, sorry about that. 8 equals, oh no. Sorry, it zoomed in real quick. And I don't want captions. I mean, I like captions, but they're not helpful right now. All right, there we go. So 8. That's 8. Okay. So let's get rid of the captions. All right. So when we're figuring out how many valence or what charge it's going to take, your elements that have fewer valence electrons, it's going to be a lot easier to kick those electrons out in order to form a cation. Whereas the elements that have more valence electrons, it's going to be harder to kick them out. In fact, you want to gain electrons, okay? So those group 1 elements, those metals, they only have 1 electron that's present. And so that 1 electron can get kicked out. And so if I lose 1 electron, I now have a positive 1 charge that would be generated because I'm down 1 negative electron. Same thing with like 2 valence electrons. If I had a party, only had 2 people show up, it's a lot easier for me to kick those 2 people out versus trying to get all these more people to come over to the party, okay? So we're going to kick those 2 electrons out. Because I've now lost 2 negative electrons, which means the balance between protons and electrons is shifted by 2, I will now have a positive 2 charge. Group 3 will have a positive 3 charge because I'm able to kick out those 3. Well, so now let's think about what happens on the other side of the chart. we're not going to focus on that group 8 just yet. Let's focus on group 7. Group 7, well, that has 7 valence electrons. So now the party that I was talking about earlier, the party is jumping, right? Now it's hard for me to get those 7 people to leave my party. And in fact, it's easier for me to go get one more person to come pack it out, okay? And so your group 7, they're going to gain an electron, and they're going to take on, because they have 1 extra electron, they're going to now be a -1. Group 6 has 6 valence electrons. Again, harder to kick the 6 out, but I can get 2 more to come on over, especially in a reaction. The metal's giving them away. I'm going to take them. All right. And so group 6 has a -2 charge. Group 5, again, easier for me to get 3 more to come on over. So it's going to be a -3. Now, group 4 can be +4 or -4, depending on who it's bonding with. Okay. And group 8, well, group 8, it doesn't want to do any of that. It's one of our noble gases. They're considered to be inert. Inert means they don't like to react with anybody. That means I don't want to give you any electrons. I don't want to take any of your electrons. And so your noble gases don't like to form ions. It would be very difficult for them to form an ion. It would need a ton of energy. Okay. And so when you're asked to figure out the cation of something or the anion of something, you're going to look at where it's located. Now, notice I focus a lot on the main group elements, the first 2 columns, and then the last 6. Didn't really talk about those transition elements. Your transition elements, just for kind of, reference, they can actually take on multiple charges, and that has to deal with actually the question that DC had asked earlier, which is around that electron configuration piece, right? Let's actually do that one, because we did iron, I think. So iron had, remember, the electron configuration was argon, 4s2, 3d, it was 3d6, okay? And so for iron, something that's in those transition metals, because of that fourth energy level, which is technically your valence, the outermost shell, but then that 3d, those d orbitals that are able to penetrate into that higher energy level, you can actually lose a lot of electrons here, which is why a lot of these metals in those transition metals have multiple charges that they might take on. And so iron can actually be like Fe2, right? Because I can kick out these 2 electrons first in the s orbital so that those go. And that's where I would get iron. So this was for iron. That's where I get iron with a 2+ charge. But it's also, I could actually come into the d orbital and kick out one of these electrons in the d. And that's where I can also get, which would make this now 4s empty 3d5. And so I could also get Fe3+. And so the moral of the story is your transition elements can have multiple charges. And so when it's, depending on who it's reacting with or bonding with, will determine how many electrons it might give up in the reacting process. Okay. I hope that helped as we were working through that. All right. And again, if you have additional questions or want to see additional content, definitely make sure to hit that QR code in the top corner so you can learn more about all the great resources that Chegg has to offer. Okay. All right. We got a few more questions. I'm going to try to get through a few more. Okay. Clear out my board. In fact, actually, I think I have an empty board. There we go. Work smarter, not harder. All right. So I see Iman 24X on TikTok. Can you go over Boyle's law? Absolutely. And I'm going to do you one better. I'm actually going to go over gas laws in general. Okay. Because gas laws, again, are a really important part that we talk about throughout chemistry classes. And in fact, I saw another question from Parker's Summer on TikTok around osmotic pressure. This is all kind of related together. Okay. And so this, when we're dealing with gases, all right, these gases, the environment that the gases are in can impact so many different properties associated with the gas itself, right? So we know gases like to expand, they like to contract, depending on if they're in hot or cold areas. Or sometimes if we change the volume that they're in, they like to get bigger or smaller, etc. And so when we're dealing with gas laws, the gas laws themselves are connecting several variables to one another. Okay. We're looking at connecting the pressure, the volume, the temperature, and then the amount that's present, the number of moles that are present. Okay. And so there are really a couple of different gas laws that we're going to deal with. So you asked about one in particular, Iman, about Boyle's law, but I think it's important to talk about a little bit of all the gas laws so you know how they're connected. There's a main formula that we're going to use that's going to help us get to all of these other gas laws that exist. And so that is what's called the ideal gas law, which is this law that it's stated as PV equals nRT, where P is your pressure, V is the volume, N is the number of moles, R is actually a gas constant, and T is the temperature in Kelvin. Okay. All right. And so I'm going to give you this background about the ideal gas law to help us get to Boyle's law, which you asked about. So ideal gas law is PV equals nRT. Well, because the R, the gas constant, is set, that equals 0.08206 liters times atmospheres divided by moles times Kelvin. When we're dealing with gases and changing the environment that it's in, whether that's increasing the temperature or changing the volume or changing the pressure, whatever we're doing, it still has to allow for the gas constant to remain constant. Okay. And so occasionally what you'll see this gas law is an expanded version of this gas law, where you're essentially saying that, okay, well, if I said that everything has to equal this constant, the R, if I rearrange this equation, that tells me that PV over N divided by T would be equal to my gas constant, right? All I'm doing is just the algebra here, dividing both sides by NT. Well, if I had one set of conditions, P1, V1, N1, T1, and then I change something in these conditions, and now I have maybe a new pressure, a new volume, maybe changing my moles or my temperature. Okay, this is where we get this expanded gas law. Okay, and so this expanded ideal gas law, where P1 V1 equals N1 T1 equals P2 V2 over N2 T2. This is, if you know these two equations, this will help you to get to all the other gas law equations that are present. Okay. And so Boyle's law, Charles' law, Avogadro's law, those are all laws that that happen when one or more of the variables is held constant, but other variables are able to change. Okay. So follow with me. All right. So Boyle's law, the question that was asked, Boyle's law is looking at the relationship between pressure and volume. Okay. And so this is basically assuming that the moles and the temperature are going to be held constant. Okay. And so why I show you the expanded gas law is because you can actually get any of the other gas laws from this expanded. You basically just you cover up the pieces that are constant, i.e. the moles and the temperature in this case. And that's going to get you your Boyle's law, which is P1 V1 equals P2 V2. Okay. All right. And the way I remember Boyle's law, so you can boil potatoes and vegetables. Again, I come up with all types of sayings, visuals to help me remember things. So I can boil potatoes and vegetables. And so that's how I remember that P and V are in this. Now, in Boyle's law, your pressure and the volume have an inverse relationship, which basically means as I increase the pressure, the volume is going to decrease, or vice versa. If I decrease the pressure, the volume would increase. Okay. And so if you had to map this, you would end up with this kind of curved relationship here. Okay. And put my pressure and volume on this scale. Okay. The other laws, so when you're doing Boyle's law, the units for pressure or volume could vary, as long as they match on both sides. So P1 and P2 have to be the same. V1, V2 have to be the same as you're solving for any problem. And you would really just read the problem, and we can do some deeper examples of this next week. But you would read the problem, figure out what you're solving for, and rearrange for the appropriate variable. Okay. I do quickly want to talk about some of the other laws. So Charles' law. Charles' law is looking at the relationship. Now, pressure and moles are held constant. So this is looking at the relationship between volume and temperature. So again, you could get that from looking here. You would just cover up the parts that are held constant. And so that gives us V1 over T1 equals V2 over T2. And so here it's important to note temperature must be in Kelvin. Okay, for any gas law problem. And so the way I remember Charles' law is that Charles Barkley, who is a basketball player, he's very tall. And so I say it like that so that I remember that it's volume over temperature. So I can boil potatoes and vegetables, and Charles Barkley is very tall. Okay. There is also Avogadro's law. So Avogadro's law is looking at the relationship between volume and moles. Pressure and temperature are held constant. And so that equation would be V1 over N1 equals V2 over N2. The way I remember this one, Avogadro sounds kind of like avocados. Avocados are very nutritious. So VN. All right. So again, just a quick way for me to remember them. And then the last law is Gay-Lussac's law. And Gay-Lussac's law is looking at the relationship between pressure and temperature. And so it would end up being P1 over T1 equals P2 over T2. Again, temperature must be in Kelvin. Now, Boyle's law is the only one of your gas laws that is an indirect relationship. All of the other ones, as your temperature increases, your volume would increase. So that's a direct relationship. Same with your moles and with your pressure and your temperature here. All would be direct relationships. Okay. We'll pick back up with these next week. I know we're just about out of time, but I do want to remind you all to scan that QR code that's in the top corner. That's going to be where you're going to find a ton of more resources that are available for you all for this topic, but also other topics as well. There's also weekly live sessions that are offered. I'll be back next Thursday at the same time, 8:30 Eastern or 5:30 Pacific time to answer more questions, but feel free to drop questions throughout the week. You can direct message me so that I can get some questions prepared for you as well. I do see, let me see if there's one I can do quickly. Yep, I see from Anastasia on TikTok, groups equal electrons, periods equals the number of orbitals. So the period actually is equaling the energy level. So not necessarily the number of orbitals per se, but it's also showing the energy level. I see when are your chemistry office hours? Every Thursday, 8:30 p.m. Eastern or 5:30 p.m. Pacific time. So same time, same place next week. And you can check me out, Larissa. Dr. J, could a three-dimensional frequency table be used to display more complex data sets? Perhaps. It depends on what kind of data you're looking at, Kevin, that you might want to use that type of table. I'm just trying to make sure. And then I see isotope from Anastasia on YouTube. So isotopes are different than ions. And so isotopes are those atoms that have a change in the number of neutrons that are in the atom. So because there's a different number of neutrons, you're going to have a different mass. Okay. I hope that helped you all today. I hope you all enjoyed today's session. Please, please, please feel free to join me again next week, next Thursday, same time, same place. You can also follow me at Gen Chem with Dr. J on YouTube and on TikTok. Drop your questions there throughout the week, and I'll be sure to answer them. Until next week, enjoy